Hello, everyone. I am Alice, and this is Mr. Macaroni. Today, I'm going to give you an overview of my summer research supervised by Professor Mona Bersu at the University of British Columbia. We worked on the signatures of electronic polarons and bipolarons in iron-based superconductors. Iron-based superconductors is a part of the family of high TC superconductors, which means that this material sees a transition to zero resistance at some critical temperature greater than 30 Kelvin. Although the mechanism for high TC superconductivity is still an area of active research, the general consensus is that we need some mechanism for two electrons to pair up, such that there is an attractive interaction where the energy of the electron pair is lower than that of the two individual electrons. In today's talk, I will give you an introduction to our material, iron arsenide, and introduce how electrons and induced dipole moments play a role in our mechanism of interaction. Next, we bring two such electrons closer together and show that this object, the bipolaron, is indeed energetically more favorable. And finally, we introduce some theoretical predictions for a laser experiment that can potentially verify the existence of polarons and bipolarons in this material. Iron arsenide is a quasi-2D structure with layers of these iron arsenide sheets stacked together. Here we show a 3D view of one slice of iron arsenide with red indicating arsenic and green indicating iron atoms. Zooming in to one unit cell of iron arsenide, we find the layer of iron is sandwiched between the two arsenic layers, and the arsenic above and below the iron plane lies on opposite diagonals of the cube. Now you may be curious to ask what is happening with these lobe shapes for the arsenic atoms. Well, that is a consequence of the induced dipole moment in these arsenic ions, which is at the heart of our interaction mechanism. We start by having an additional electron on these iron sites, which produces an electric field. The arsenic ions get polarized and form a dipole moment pointing towards this electron in the center of the cube. Quantum mechanically, we can describe these dipole interactions using a transition between orbitals. The arsenic ions start in their 5s configuration, and the holes have a tendency to transition towards a 4p orbital that points towards this extra electron in the center. This interaction has an associated energy G, which is negative and linearly proportional to the strength of the electric field. So far, our model only concerns the one electron and the first ring of 4 arsenic ions around it. We can always make the Coulomb interaction more longer ranged and add the second and third ring of arsenic ions into this polarization mechanism. There will be different interaction energies associated with the second and the third ring, and the energies fall off with 1 over r squared as the electric field is decaying with distance. So far, we've been describing the scenario with one charge polarizing arsenic ions around it, and this is called a free polaron. But to obtain a pairing mechanism, we need to bring two such polarons together. In that case, there will be arsenic ions, shown in the bottom right diagram, sharing electric fields from both charges on neighboring iron sites. And the strength and direction of the electric field will be different, and hence the energy associated with the dipole interaction will be different as well. We call this scenario, where the two polarons are overlapping, an electronic bipolaron. In the next few slides, I am going to produce some plots comparing the bipolaron energies for different rings of arsenic ions relative to the energy of two free polarons. First, we're going to look at the case where the electron only polarizes the first ring of arsenic around them. And here we have the 2D picture of the interaction, and the two shaded arsenic ions are sharing electric field from both charges. On the right, we graph the ground state energy of the bipolaron relative to that of two free polarons across a range of values, where the omega on the x-axis is the gap between s and p orbital taken from band structure calculations in literature. And we find that for this configuration, the bipolaron has a negative energy of -1 electron volts lower than two free polarons, indicating that this is indeed an attractive interaction. Going further and allowing each of these electrons to induce dipole moments in arsenic up to the second ring, we obtain many more shared charges and a much more attractive interaction, shown by this dashed line, with more than 4 electron volts of energy advantage for the bipolaron to form. We can always move further into the third ring of arsenic ions, but the relative changes in energy are much smaller, despite the many more arsenic ions that are sharing electric fields. This is because the electric fields are falling off very quickly with distance, and even faster if we were to include screening in this model, which I do not have in this graph. So far, I have introduced our model and why we believe it provides an attractive pairing mechanism between these two electrons. For the next half of the talk, I will provide some theoretical predictions on how we can measure some of these signatures of polarons and bipolarons using a laser experiment. Recall that our mechanism involves these electrons introducing electric fields that induce dipole moments on nearby arsenic ions. However, we can also ask experimentalists to shine laser on the material, which effectively applies an external electric field and perturbs the existing dipole moments. When we think of an oscillating electric field, there are two important parameters. One is the magnitude, and the other is the frequency of oscillation. The magnitude can be calculated from the laser intensity to be 10 to the power of 6 volts per meter, which is similar to the field strength of a lightning strike. And in our model, this translates to the energy associated with the dipole interaction of only 0.27 millielectron volts. Meanwhile, the frequency of the laser, which is typically expressed as an energy, is 6 electron volts for the experiment. And this is an interesting frequency or energy because it is close to the resonant frequency of the system, lying at 6.9 electron volts. And that's the energy difference between the first excited state and the ground state for a polaron. Now we're going to take a look at how the polarons behave without any external laser or electric field. The arrows on these diagrams indicate the direction of the dipole moment for the ground state and first and second excited states. In particular, note how the first excited state contains dipole moments that are perpendicular, and the second excited state contains dipole moments that are anti-parallel to the dipole moments of the ground state. Now let us turn on the laser in this top left to bottom right direction, indicated by the blue arrow on the left diagram. Observing the two arsenic ions shown on the diagram, we expect to see some excitations into the first excited state due to the direction of the laser. And this is captured by the graph on the right. The wave function magnitude squared captures the probability of finding the arsenic in this state, and the horizontal axis is time, normalized such that 1 means 1 period of the laser oscillation. And as we started, the system is fully in its ground state, indicated by the blue curve, and the probability for it to be in the first excited state, indicated by the orange curve, increases to almost 20% after 3 periods of the laser oscillation. An observation you may also have is this envelope frequency that appears to have 6 times the period of the laser frequency. And this is due to beats forming between the laser frequency and the resonance frequency of the system. And similarly, observing the other two arsenic ions in the polaron, we observe some more excitation into the second excited state. However, since the second excited state has a higher energy cost, the probability increase here is not as evident as the last one. And finally, we're going to study the two arsenic ions that are shared in the bipolaron. For the bipolarons, the probability changes are again quite small, owing to the fact that the first excited state lies at a higher energy of 8 electron volts for these two arsenic ions, and the direction of the oscillating field is not really parallel to the excited state. One important conclusion we can derive from that is that it is much harder for the laser to excite the bipolaron, and there will be a much smaller change in energy during this laser oscillation. And this is indeed what we observe on this plot of polaron and bipolaron energy on the slide. The energy of the two free polarons is shown in red, and the energy of the bipolaron is shown in blue. Recall that we've only inputted a laser intensity, which can be translated to an interaction energy of 0.27 millielectron volts. However, due to the interactions of polarons and bipolarons, we're expecting to see a almost 10 electron volts difference between the two configurations, which is very large and measurable effect for an experiment. Throughout this talk, I have introduced to you a mechanism of pairing that arises with electrons inducing dipole moments on neighboring arsenic ions. I have demonstrated that for a variety of values, this interaction is indeed attractive. And I have provided some simulation predictions on how a laser or oscillating electric field can produce a measurable change in the energy of the system. Our collaborator will be performing this experiment in the coming year, and we're excited to see whether these polarons and bipolaron interactions will indeed manifest themselves in experiment. With that, I'd like to end by thanking my supervisor, Mona Versu, and many of her past and current students with this photo we have taken at the Superconductivity Conference in Vancouver this summer. I would also like to thank the financial support from WorkLearn International Undergraduate Research Award and the QMI Quantum Matter Institute at UBC for an amazing summer. Thank you for watching.